Welcome to The Explainer. Today we're diving into something called the discrete logic of digital security. We're going to demystify exactly how your personal data is actually kept safe online. You know, we constantly hear buzzwords like encryption and cybersecurity, right? And it's so easy to just assume they require this impossibly high level of mathematical genius. But the reality? Well, it's actually much more grounded than that. And honestly, it's way more fascinating.
So how does a simple puzzle hold the secret to an absolutely unbreakable password? That's our hook for today. We're bridging the super relatable everyday world of recreational puzzles, the kind you might literally solve sitting at your kitchen table, with the incredibly high-stakes realm of digital cryptography. Now, I know that sounds like a massive leap. Like, how on earth could a basic logic game relate to keeping advanced threat actors out of your bank account? Well, stick with me because by the end of this explainer, the intimate connection between these two worlds is going to be absolutely crystal clear.
All right, let's jump right into Section 1, the logic of puzzles.
Consider this perspective from Professor Laszlo Lovaas. He's a brilliant mathematician who actually teaches entirely through puzzles. He says, and I quote, "Counting and logic aren't just for school, they're the tools used to secure our data and encrypt our messages." I love this because it completely disarms our usual assumptions. I mean, we usually picture data security as this impenetrable, glowing wall of complex code, right? But at its absolute core, the whole shebang is built on basic counting and logical reasoning. When you strip away the confusing syntax of programming languages, what you're left with is the simple elegance of solving a puzzle. It's just about finding paths, understanding the limits, and arranging variables to build an insurmountable barrier for anyone who doesn't happen to have the key. Moving right along to Section 2, continuous curves versus discrete steps.
So when we think of traditional math, the stuff we spent years sweating over in school, we usually picture continuous curves. Think about geometry or calculus. It's all about smooth, unbroken lines, right? Infinite flowing values moving seamlessly from one single point to the next. But computer science, it operates completely differently. It focuses strictly on distinct, individual, discrete steps. There are literally no smooth curves in computer logic. If traditional math is like a dimmer switch smoothly sliding up and down, computer science math is an absolute on-off light switch. Boom, on or off. It's a world of ones and zeros, trues and falses, where absolutely everything has to be quantified into separate, distinct units.
And that brings us to discrete mathematics, which is simply the study of distinct, individual steps rather than continuous values. Now, this isn't just some niche, obscure branch of numbers. No, it is the absolute bedrock of modern computing. Think about it. If you want a processor to understand a command or encrypt a file or secure a whole network, you can't use continuous, infinite curves. A computer fundamentally runs on electrical pulses, right? It either receives a signal or it doesn't. So to actually communicate with it and harness all that processing power, we have to break every single problem down into these exact discrete steps. Basically, we have to translate the continuous real world into the discrete digital world.
Let's unpack this a little further in Section 3, the science of counting.
So, the engine actually driving all this discrete logic is called combinatorics. That's the fundamental mechanism of calculating various counting possibilities. Remember those recreational kitchen table puzzles we talked about earlier? Well, combinatorics is really just the science of counting without having to agonizingly count every single item one by one. It's the mathematical framework we use to look at a set of distinct, discrete items, say the letters, numbers, and symbols on your keyboard, and calculate exactly how many unique ways they can be arranged. It gives us the tools to map out the total universe of possibilities in any given scenario. And frankly, that is the foundational blueprint for building truly robust digital security.
We are talking trillions upon trillions of possibilities here. That's what happens when you apply combinatorics to a digital password. When you structure a cryptographic key correctly, the number of distinct counting possibilities literally explodes. And this massive scale, that is your actual defense. It's exactly what makes modern encryption mathematically unbreakable. A hacker's supercomputer can't just brute force guess your password if there are trillions upon trillions of discrete combinations to check. The sheer weight of the math becomes your ultimate shield. You are literally hiding your data behind an ocean of mathematical probability, which turns the simple act of counting into an absolute impenetrable fortress. Pretty wild, right?
Which brings us to our final section. Section 4, securing our digital world.
Let's tie it all together, because this creates a really direct, logical progression from a super simple concept right up to a robust security system. Step 1. We start by applying simple logical reasoning, exactly like you would when solving a recreational puzzle. You identify the rules of the game and the constraints you're working within.
Then, step 2, we use combinatorics to calculate the massive number of distinct counting possibilities generated by those rules. Step 3, by leveraging those trillions of possibilities, we formulate unbreakable digital encryption. And finally, step 4, that encryption successfully safeguards our most sensitive information. It really is this seamless journey from foundational logic straight to a practical, bulletproof defense.
So ultimately, simple mathematical problems provide the exact tools we need for safeguarding sensitive information in a digital environment. The mechanics behind data security aren't magic. They aren't impossibly complex algorithms conjured out of thin air by a wizard. They're just fundamental, elegant mathematical concepts, distinct steps, and counting possibilities applied brilliantly to our modern digital lives. Once you actually understand the discrete logic beneath it all, those intimidating digital walls suddenly transform into beautiful, mathematically sound puzzles.
Which leaves us with one incredibly thought-provoking question to wrap up this explainer. If the security of your entire digital life, we're talking your bank accounts, your private messages, your very identity, if all of that relies simply on the science of counting and discrete steps, well, what other incredibly complex systems in our world are really just puzzles waiting to be solved?